section, we're going to tackle short circuit analysis based on ANSI C37 standards. Before we start, let's have some overview on short circuit current. There are several types of short circuit faults. These are three-phase ungrounded fault, three-phase grounded fault, phase-to-phase ungrounded fault, phase-to-phase grounded fault, and phase-to-ground fault. Line-to-ground fault is in utility systems can range from a few percent to perhaps 115% of three-phase fault current. This will occur only if the zero sequence reactance is less than the positive sequence reactance. 85% of all faults in the power systems are line-to-ground faults. Line-to-ground fault is rarely greater than three-phase fault in industrial systems. Normally, line-to-ground fault is roughly equal to 87% of three-phase fault. The three-phase fault current condition is usually the only one being considered in an industrial systems, since this type of fault generally results in maximum current. The purpose of short circuit studies: to verify the protective device closing and latching capability, to verify the protective device interrupting capability, to shield equipment from large mechanical forces, thermal stress or I2T protection of equipment, fault data obtained used for relay coordination settings. System components involved in short circuit calculations. These are power distribution utility company supply, in-plant generators, transformers and reactors by using their negative tolerance, feeder cables, bus duct systems, and overhead lines at their lower temperature limit, synchronous and induction motors, protective devices, zero sequence admittance from static load, and line cable. Elements that contribute current to a short circuit. These are generator, power grid, synchronous and individual and induction motors, lamp loads. By the way, lamp load is composed of static loads and motor loads. These are inverters and zero sequence current from grounded Y-delta connected transformer. Elements do not contribute current in power station. These are static loads, the MOVs or the motor operated valves, all shunt admittance connected branches such as capacitors and harmonic filters. Short circuit phenomenon. The intensity of short circuit current is directly related to the size and capacity of power sources, that is, utility generators and motors, which is typically independent of the load current of the circuit. AC synchronous and induction motors, generators, and utility ties are the main element sources of short circuit currents. During fault, synchronous and induction motors will act as generators and will supply current to the short circuit based at stored electrical energy in them. Actually, for ANSI study, we have three impedance networks that are being used and formed to calculate momentary, interrupting, and steady-state short circuit currents. These are 1/2 cycle network, the 1.5 to 4 cycle network, and the 30 cycle network. For 1/2 cycle network, This is the network used to calculate momentary short circuit current and protective device duties at the 1/2 cycle after the fault. These are the type of devices. The HV circuit breaker, the LV circuit breaker, the fuse, the switchgear and MCC, and the relay. For HV circuit breaker, the duty is the closing and latching capability. For the low voltage circuit breaker, its duty is for the interrupting capability. And also for the fuse, the duty is also for the interrupting capability. For the switchgear and MCC, this is used for the busbar bracing. And for the relay, the duty is for the instantaneous settings. For 1.5 to 4 cycle network, this network is used to calculate the interrupting short circuit current and protective device duties 1.5 to 4 cycles after the fault. The type of the device is only high voltage circuit breaker, and its duty is for the interrupting capability. For the 30 cycle network, this is the network used to calculate the steady state short circuit current and duties for some of the protective devices at 30 cycles after the fault. The type of the device is for the relay only, and its duty is for the overcurrent setting. Okay? From your screen, we have here a power single line diagram with a different voltages level. So we have one for high voltage, we have here 115 kV. For the medium voltage, we have here 13.8 kV. Downstream here, we will check it later. We'll have here 4.16 kV. And for the low voltage, we have 480 volts. Okay. So here, we have here all the information for our power grid. To provide this information here from your screen, just go and click this display options, okay? From here, for example, on the power grid, okay, where's the power? This is the power grid. So I check here the ID, the rating, the kV, the amperage, the connection, and the impedance. That's why we have all the information from here, okay? So for the power grid, we have the MBA short circuit of 2000, and it's rated 115 kV, 10 kiloamperes, and this is the impedance. Okay, and we have here on the left side of your screen, we have the 3-winding transformer. The primary rating is 20 MVA, 115 kV, and the impedance is 7.5. The secondary is 10 MVA, 13.8 kV, and the impedance also is 7.5. While for the tertiary, it's rated 10 MVA, 13.8 kV, and the impedance is 14.5%. One of the under the secondary side of this 3-winding transformer, we have here the bus 2, which is 13.8 kV bus, and the lamp load is rated 5 MVA. To check this, what is inside for the lamp load, in our case study, lamp load is composed of 80% motor and 20% static loads. You just click OK. Okay. On the tertiary side of the transformer, it's connected to bus 3. Okay, it's also 13.8 kV. And there's composite network. We will check that one. Okay. So we have here a 2-winding transformer connected directly to the 115 kV bus. We have here 15 MVA 2-winding transformer. Rated, the voltage is 115 kV, stepped down to 13.8 kV, and the impedance is 6.5%. Okay, here we have here a certain generator. The function for this one is for the voltage control. It's rated 10 megawatt, okay, and of course 13.8 kV, and the subtransient reactance is 19%. Okay, now we have here a composite network. To check this one inside, just double click this. Okay, so we have here a double-ended substation. So we have here for bus 5 and the bus 6. So we have here two of the same rating of the transformer, the T3 and the T4. It's a two-winding transformer. It's rated 5 MVA. And the voltage is 13.8 kV, step down to 4.16 kV. And the impedance both are 6.5%. The tapping for the primary is negative 1.25%. Okay, so for the T3 transformer, it's connected to bus 5, rated 4.16 kV. Okay, we have here a synchronous motor, two numbers of 2000 horsepower synchronous motor. Okay, and here on the other side, on the bus 6, we have here an induction motor is also 2000 horsepower. Okay, and we have here a step down transformer to NBA 4.16 kV to 480 volts, and impedance is 7%, and the tapping on the primary is negative 2.5%. Okay, so from here, from bus 8, there is a composite motor connection from here. We're going to check that one, okay, later. Okay, for the bus 7, we have here uh, four numbers of 500 horsepower in induction motor. And here we have the static load rated to MVA. Okay, let's check what is inside from this composite motor. Okay, just double click. Okay, so we have four loads, actually four main loads here. First one, we have here the induction motor rated four numbers of 200 horsepower. Okay, this one is five numbers of 100 horsepower induction motor. Okay, we have also here one number 250 horsepower motor, induction motor. And here we have the static load, which is being protected by fuse, which is rated 1 MVA. Okay, so let's go to the 115 kV substation. Just double click this one. Again, double click this one. Hold on. Okay, so we have right now in the 150 kV substation. So now we're going to perform short circuit analysis, okay, adopting, of course, the ANSI C37 series standards. Okay, so we're going to do bus bracing for all the buses, 450 kV bus, for the 13.8 kV bus, for the 4.16 kV bus, and downstream for the 480 volt bus. And also for the breaker, we're going to assign the duty or some current duty short circuit capability of the circuit breaker. Okay, for the CB1, okay, just double click. Okay, and we are, let's go to rating from here. Okay, so from here, I'll select the library here. Okay, okay, so I use the ABB circuit breaker. From the library, it's already provided here the continuous ampere, the maximum kV. Since this is 115 kV, we have 121 kV, the rated interrupting kiloamperes, which is 20 kiloampere. We have here, because the high voltage circuit breaker is, the capability is being based on the closing and latching RMS and closing and latching peak. So from here, the manufacturer already provided their circuit breaker these values. Okay, so just click OK for this. Here, for the sake of discussion, I'm going to change this one. Into, now it's 20 kiloamperes. I'll change this one into 12 kiloamperes. And let's check it later what will happen. Okay, so just click this one. Okay. And for the 150 kV pass, okay, so let's go to the rating. Okay, here for the bracing, if you put other here, this will be becoming blank. Okay, you need to provide, for example, here, okay, let's say open air, okay, for the bus. Okay, so we have here 26 kiloamperes. Okay, this is ETAP or automatically assigned for the bracing here. The asymmetrical RMS value is 26 kiloamperes and converted into peak because this is for the high voltage bus. We have here 43.88. This is only temporary assignment. We'll check it later because once we run the source circuit analysis, there will be a flag if there is abnormalities, whether our bus bracing is not enough against the actual short circuit current in the power system. Okay, just let's just press this one. Okay, and we have here for the CB2 circuit breaker number 2. Let's click this one here. Okay, and for the rating here, I took also from the library. Okay, I assign ABB here, and the model of the circuit breaker is 121PM20. This is automatically given by the library. Okay, this information is from the actual circuit breaker of ABB. Okay, so we have here the rated interrupting current, which is 20 kiloamperes, the C and L RMS, and C and L peak. So we're not going to change from here. Let's check that one later. If this one is sufficient for the actual short circuit current, just click OK for this. Okay, and CB4, okay, rating. We assign here the ABB manufacturer. Also, the rated interrupting is 20 kiloamperes. The C and L RMS 32 and the C and L peak 54. So let's just click this one. Okay. Okay. So from here, let's go downstream for the CB3. Let's open this. Okay. And we have the rating here. Everything here I choose ABB breaker. Okay. So we have here the rated interrupting is 37 kiloamperes. Okay. We have here also the C and L RMS is 80. This is automatically assigned. This is the properties of this particular circuit breaker. And the C and L peak is 129.6 kiloamperes. So just click OK for this. For the CB5, okay. Let's click this. Let's go to the rating. Okay. So the rated interrupting is 18 kiloamperes. The C and L RMS is 36.8 kA and the C and L peak is 62 kiloamperes. So let's click this one. Okay. For CB6, okay. So we have here the rating. Okay. And this different model right now is rated 18 kiloamperes. Okay, and the C and L RMS is 36.8 kiloamperes, and C and L peak is 62 kiloamperes. What we have here, this is only temporary because once we run the short circuit analysis, this will be verified whether this rated interrupting capability is enough for the actual short circuit. So click OK. So I think we have done all the circuit breaker from here, and we'll do the bus bracing also for the bus 2, 3, and 4. For the bus 2, okay, let's go to rating. We assign this one as switch gear, okay, switch gear, and the bracing that we temporarily assigned The symmetrical RMS is 37 kiloamperes, and the peak, once you assign here the value in the asymmetrical RMS, ETAP automatically calculate the peak value. Okay, we have here the 62.44 kiloamperes. Okay, this is for the bus 2. For the bus 3, okay, let's click this. Rating. We have also the same, is switchgear, 37 kiloamperes, and the peak is 62.44 kiloamperes. Click OK. And for the bus 4, let's click this. Okay. The rating, the same, asymmetrical RMS, 37 kiloamperes. The peak is 62.44 kiloamperes. Okay. Let's click this, double click this network from here, composite network. Okay. So we don't have breaker from here. Here, let's go first to the bus 5. Okay. The bus 5. The rating here is 25. We assign here 25 kiloamperes. Okay. The peak value is 42.19 kiloamperes. Okay. Let's click OK. The same also for the for the bus 6. Okay. The rating here is 58. Okay. As the symmetrical RMS is 58, the peak is 97.88. Okay. And let's click this one. Okay. This is for the bus 6. Okay. And let's finish all the buses from here. So for the 7 and 8, okay, for the 7, the rating here is 50 kiloamperes. Okay. And for the peak is 84.38 kiloamperes. For the bus 8, the rating is 27, 20, let's say, let's put this one as 20, okay. This we have here, because this is 400 low voltage bus. So for the low voltage bus, we are braced, it is being braced on symmetrical RMS and asymmetrical RMS. Okay. So for bus 8, we assign here 22 kiloamperes, and the asymmetrical RMS automatically calculated by ETAP is 27.4 kiloamperes. Okay. So I think we have finished all the buses. Okay. So now for the breaker. Okay. So for breaker number CB8. So the rating here, we have here also ABB, and the model what we selected is 5AD V36. We have here the rated interrupting is 29 kiloamperes. CNL peak is 97. CNL RMS is 57.6 kiloamperes. Let's press OK. CV11. Okay. The rating is 20. The rated interrupting rating is 29 kiloamperes. CNL RMS 57.6 and CNL peak 97 kiloamperes. Okay. Okay. Just press that one. Okay. And we have here 3. Okay. Let's first CB9. Click this CB9. Okay. We have here is also rated 29 kiloamperes. CNL RMS 57.6 kiloamperes and CNL peak 97 kiloamperes. You know, why I am highlighting this rated interrupting CNL RMS and CNL peak. Later, I will explain it to you. Okay? We have CB10 here. Okay? Rated interrupting is 29 kiloamperes. CNL RMS 57.6 also kiloamperes. CNL peak is 97 kiloamperes. Okay. And then for the CV12, okay. Oh, so for the CV12, okay, for the CV2, let's provide an exemption for this. We're not going to check the social capability of this CV12. Okay, will go downstream. Okay, let's double click this composite motor. Okay, from here we're going to provide here the perform first the bus bracing for the okay, so it's already done for the bus 8. So we'll go for the circuit breaker. Okay, for the CB13, okay, let's go for the rating. Here, interacting key, since right now this is for the low voltage, it's not asking anymore for the closing and latching, because the closing and latching capability that is only applied for the medium voltage circuit breaker and high voltage circuit breaker. Here, it is only asking for interrupting key. We have here assigned 42 kiloamperes. So just click OK. CB14. We have here 66 kiloamperes, interrupting KA. For the CB15, we have here 65 kiloamperes, okay. And for this static load, okay. Actually, this information here I took from the library taken from the brush manufacturer. Initially, it was in 200 kiloamperes. I changed this one into 30 kiloamperes. Anyway, we're going to check this one, what will happen, okay? And let's click OK. And let's go to the main single line diagram on the 115 kV substation. Just hold on. Okay, it's take a little bit time. Okay, so we have here this system right now is ready for that we can perform right now short circuit analysis. Let's go to this symbol here from this one, short circuit, and click this one here. Okay. Before we start, let's have some small discussion on what are the functions for here. We see here maximum, we have here the 1.5 to 4 cycle short circuit. We have here the minimum, and we have here for the duty. Okay, so this we'll discuss first, this one, okay? The run 3-phase device duty based on ANSI 37 standard. Okay. Click on this button to perform a 3-phase fault study per ANSI 37 standard. This study calculates momentary symmetrical and asymmetrical RMS. Momentary symmetrical crest, interrupting symmetrical RMS, and interrupting adjusted symmetrical RMS short circuit current at faulted buses. ETAP checks the protective device rated close and latching adjusted interrupting capacities against the fault currents and flags inadequate devices. Generators and motors are modeled by their positive sequence subtransient reactance. This is for the duty, run 3-phase device duty. For this, the run 3-phase, line to ground, line to line, line to line ground in 1/2 cycle. We call this one as maximum short circuit current. By clicking this button to perform 3-phase, line to ground, line to line to ground fault studies per ANSI standards. This study calculates short circuit currents and their RMS values at 1/2 cycle at faulted buses, which are considered the maximum short circuit current. Generators and motors are modeled by their positive, negative, and zero sequence subtransient reactance. Generator motor and transformer grounding types, and winding connections are taken into consideration when constructing system positive, negative, and zero sequence networks. Any adjustment for the impedance is taken as negative in order to produce smaller impedance, and this yields higher short circuit currents. Okay, next, this one, run three-phase, line to ground, line to line ground, 1.5 to 4 cycle. By clicking this button, to perform three-phase line to line, as what mentioned earlier, okay, this study calculates short circuit currents and their RMS values between 1.5 to 4 cycles at the faulted buses. Generators are modeled by their positive, negative, and zero sequence subtransient reactance, and motors are modeled by their positive, negative, and zero sequence transient reactance. Generator, motor, transformer grounding types, and winding connections are taken also into considerations when constructing system positive, negative, and zero sequential networks. Any adjustment for the impedance is taken as negative in order to produce smaller impedance and thus yield higher short circuit currents. Okay. Lastly, we have here the minimum short circuit current. Okay. This study calculates short circuit currents in their RMS values at 30 cycles at faulted bus. Generators are modeled by their positive, negative, and zero sequence reactance, and short circuit current contributions from motors are ignored. Generator and transformer grounding types and winding connections are taken into consideration when constructing system positive, negative, and zero sequence impedance. Motors, any impedance adjustment can be applied as negative or positive. Okay, so before we proceed that, okay, I open this comparison of device rating and short circuit study. ETAP Power Station compares the rating of protective devices and bus bars with the fault duties on the bus. The comparison results are listed in the summary page of the output report. Later, we're going to open this output report to discuss the value or the output for our study. The device rating and fault duty used in this comparison are shown below. So we have here, okay, the device duty for example, the high voltage bus bracing, the device capability we required one. First, the asymmetrical KA RMS and the asymmetrical KA Crest. The calculated short circuit study will be based on asymmetrical KA RMS and asymmetrical KA Crest respectively. For the low voltage bus bracing, the device capability has to be with in line with symmetrical KA RMS and asymmetrical KA RMS. The calculated short circuit duty is based on symmetrical KA RMS and asymmetrical KA RMS. This is for the bus bracing. Okay, for high voltage circuit breaker, okay, we have here the close and latching capability KA RMS and close and latching capability KA Crest. For the KA RMS, the calculated short circuit duty is we need to check the asymmetrical KA RMS. For the KA Crest, we need also to check the symmetrical KA Crest. Okay. For the interrupting capability of the circuit breaker, for the high voltage circuit breaker, okay, so that for the device capability in terms of interrupting, we need to check the adjusted KA. For the low voltage circuit breaker, we have also here rated interrupting KA. The same, we need to check also the adjusted KA. Okay, let's go to our power system single line diagram. Now, let's go to this button, okay, and let's start now running the short circuit analysis. Okay, So like this, let's check if there's any abnormalities in the system. Okay, so we have here ANSI short circuit analyzer. So let's open this one by clicking this. A little bit time, it's taking a little bit time. Just hold on. Okay, so let's go first to the buses. Okay. Okay. We have here the bus 5. Okay. For the bus 5, okay, initially we have here the asymmetrical KA RMS and we have the red flag here. It means, what we have assigned, the actual asymmetrical KA RMS and the peak KA RMS is higher. See, in red, this is critical because we assign here 100% and the marginal here, we assign 80%, meaning 80%, our device capability is 25% higher on the actual short circuit current. Okay, so here we have two buses under red flag here. We have here bus 5 and bus 8 here because this bus 5 is in 4.16 kV. It is being based on asymmetrical KA and peak KA current. For the low voltage, we have here 480 volts. That's bus for the low voltage. It has to be based on symmetrical KA and asymmetrical current. Okay, so the problem is on bus 5 and bus 8. So let's rectify this. Okay, first, okay, let's click this one. Okay, and let's go to the bus. That was bus 5 and bus 8, right? Okay, at the bottom is 4.16 kV. Okay, we have here, let's say, let's assign here, let's change this one, the symmetrical RMS to be, let's say, 58 kiloamperes. Okay, imagine, see, the peak is automatically calculated by ETAP. And let's click this one. Okay, and also for the low voltage bus 8. Okay, and let's go to the rating. Let's change this one. Let's say, okay, since this is low voltage bus, let's go to symmetrical RMS here. Let's change this one 65 kiloamperes. Then asymmetrical RMS already automatically calculated by ETAP. Okay, and let's click OK from here. Okay, so let's check it again. Let's run the short circuit study. Okay, and let's open the ANSI short circuit analyzer from here. Okay, see, right now the red flag have been removed already. Okay, so from here, if you can, meaning the bus bracing, the short circuit withstand capability of our bus bar is 25% higher on minimum. This is 25% minimum higher on the actual short circuit on the power system. Here, we have already resolved the issues on the buses. Okay? And let's go to the high voltage circuit breaker from here. Anyway, when you want to have this information from here, just check all this one here. Okay? See, from here, it's already checked. We have symmetrical, asymmetrical, peak, multiplying factor, XR ratio. Okay. So, we have here also, please see, if you check this type. We have here for the buses, we have here the open air. This is for the 150 kV substation, and we have the switch gear for 13.8 kV and 4.16 kV, and 480 volts. We assign MCC here. So just click this area here. Okay. Now let's go to the high voltage circuit breaker. For the high voltage circuit breaker, we have the red flag from here. See? The interrupting adjusted symmetrical current is 13.00 kiloamperes. Initially, we assigned, when we selected before the CB1, it was 20 kiloamperes. Then, we changed into 12 kiloamperes to verify whether the 12 kiloamperes we have here. See, 12 kiloamperes, whether that one is enough. But the actual interrupting adjusted symmetrical current is 13.003 kiloamperes. So that's why it gives a red flag here. The rest are okay. So there was no red flag. Okay. So our marginal value here is also 80%. Okay. So just click OK from here, and let's change. Let's go to the CB1. Okay, this is our CB1 rating. Okay, so here we'll change into 20 kiloamperes. Okay. Okay, let's check the other abnormalities in the other circuit breaker. Okay. For the CB1, it's here, right? So let's go to the low voltage circuit breaker. Okay, for the low voltage circuit breaker, we have an issue on the CB13, which is 42 kiloamperes, and the actual current is 43. Short circuit current is 43.12 amperes. This is the interrupting adjusted symmetrical. Okay. So this is for the CB13. Okay. And also let's check for the fuse. For the fuse, earlier, this fuse actually is rated 200 kiloamperes, but we changed the rated interrupting capacity into 30 kiloamperes. But the actual interrupting adjusted symmetrical current is 43.12 kiloamperes. Okay, so we still have to change the CB13 and the fuse. Okay, just click OK this one. Okay, let's go to CB13. Okay, let's go from here. Okay, so this is CB13. Okay, CB13 from here. The rating, we're going to change this one. Let's see, 65 kiloamperes. Okay. And the fuse, it was the actual interrupting for this fuse, for this particular type of fuse, is 200 kiloamperes. So let's go to 200 kiloamperes. Okay. And let's click OK for this. Okay. Again, we're going to run the short circuit study. Okay, click this one, the duty. Okay. And let's open again the short circuit analyzer. Okay. Okay. From here, see? There's no red flag anymore. So we have resolved the issue for the fuse. Okay, let's go to the low voltage circuit breaker. Nothing also here. There's no critical and marginal flags here. Okay, for the high voltage circuit breaker. Let's check it from here. The issue is on the CB1, right? And we have changed this one into 20 kiloamperes. Nothing also from here anymore for the buses. For the buses, we have the issue on the bus 5 and bus 8. Nothing also. So everything now has been resolved. Okay. Right now, we're going to check. Let's click this one. Okay. We're going to check right now the report manager. By clicking this one, we will have the report manager. Okay. By this. Okay. Just click this complete. Okay. And this PDF. And you have to click OK. So, we have here okay. So, this is the actual report na. Now, this is the summary. We went directly to the summary right now. Okay. So, from here, okay, for example, for the bus 1, we have here the open type is open air. Okay. So, the device capability is asymmetrical KA RMS and asymmetrical KA peak. So, the value for the actual short circuit current on the asymmetrical value is we have only the actual short circuit current 17.593 kiloamperes. What we propose is 26 kiloamperes. Asymmetrical KA peak, we have here 43.880. The actual asymmetrical KA peak is 29.003. That's why now our device capability is suitable enough for the actual short circuit current. This is for the bus bar. For example, for the, let's see here, the CB3, for the circuit breaker rated 13.8 kV. Okay, it is also, the device capability is also being based on the asymmetrical KA RMS and asymmetrical KA peak. Okay, for the CB3, okay, the asymmetrical KA RMS, okay, let's go back from that one, is 17.523 kiloamperes, while for asymmetrical KA peak is 29. We provided this breaker is rated 37 kiloamperes with respect to asymmetrical KRMS and around 62.44 kiloamperes with respect to asymmetrical KRMS. So, right now, for the bus, for the medium voltage and high voltage circuit breaker, the device capability is based in two areas: asymmetrical KRMS and asymmetrical K-peak. Okay. But we have here on our 480 volt bus, in the low voltage for the bus, low voltage here, we have here the device capability is being adopted is symmetrical KRMS and asymmetrical KARMS. That's why here for the symmetrical KRMS we have 65 kiloamperes. The actual symmetrical KRMS is equal to 13.542 amperes. And the asymmetrical KRMS, you have here 57.772. The corresponding asymmetrical KRMS for the symmetrical of KRMS of 65 kiloamperes is 81.1 kiloamperes. Okay, let's go to the next page. We have here the interrupting duty of the bus and also for the circuit breaker. For example, for the this is only for the for the circuit breaker. It's only interrupting duty. This one, but the bus is not included from this one. Okay. Example here for the CB1. Okay. We have here the device capability. We have here the adjusted. We have here. We'll go to the device capability of 20 kiloamperes. Okay, but the actual, okay, the adjusted system KRMS actual is 13.003 kiloamperes. So this capability this 22 kiloamperes, since we assign that the marginal value to be 80%, this is 25% higher than the actual short circuit current. Okay, so right now, we're going to uh, verify right now. Okay, from here. Okay, okay. So let's go to the original. Let's go to the 115 kV bus. Okay. We need also to investigate the maximum short circuit current, because here this is only, when you run this duty, is only running for 3-phase. But we need to investigate also on the line to ground, line to line, and double line to ground. Okay, whether uh, whether this whether these short circuit currents are higher or smaller than the 3-phase short circuit current. Okay, so just click this maximum short circuit current button and let's run the short circuit again. Okay, and let's check the report. Let's check the report manager. Let's go it from here. So we have here, this is one cycle 3-phase, one cycle network, 3-phase, line to ground, line to line, double line to ground fault currents. Okay, for let's check right now. Okay, for bus 1, you see here, this is for the 115 kV bus. We have here the 3-phase is 10.557 kiloamperes. You check here, the line to ground fault is 10.82. So line to ground fault is slightly higher than the 3-phase. And also here, okay, line to line fault is okay. Also here, the double line to ground fault is slightly higher to the 3-phase. For bus 2, we have here 10.98 for the 3-phase. And line to ground is slightly lower, 10.657 kiloamperes. Line to line, this is also lower. And double line to ground is slightly lower compared to 3-phase. So here, this system, we have here only bus 4 and bus 1, the line to ground and the double line to ground, the short circuit current is higher than the 3-phase fault. What's the reason for that one? Okay, as what I have mentioned before earlier, line to ground fault in utility systems can range from a few percent to perhaps 115% of 3-phase fault current. Okay, this will occur only if, meaning if the line to ground fault or line to ground fault is higher than 3-phase. This will occur only when the zero sequence reactance is less than the positive sequence reactance. Okay, so that's the reason why we have this value that the line to ground fault is higher than the 3-phase fault. One of the reasons for that one is the type of grounding we have. Because if check from here, the bus 1 is for the power grid, is solidly grounded. Normally, it's having neutral grounding resistor. And the bus 4 also, this is for the, okay, let's check from here. This one. This is our bus 4. We have generator from here. This, let's check what type of grounding we have here. Okay. Let's check the generator grounding, this one. Okay. Here, our grounding connection is solid. Okay. So this is the reason why that our line to ground fault is higher than the 3-phase fault. Okay. And then, let's provide, okay, let's check right now. Let's do another simulation. Okay. Except for the power grid. Okay. So, let's provide here a resistor. Neutral grounding resistor. Okay, let's provide, for example, a loop a low impedance, low resistance resistor here. Let's see. Normally, low resistance resistor range from 200 to 1,000 amperes. So, by 10 megawatt, let's say around 600 amperes from here. Okay, now the resistance around 13.2, 27 ohms. Okay, and let's simulate again. Okay, so let's go to the shoe circuit and let's run the maximum. Okay, the maximum show circuit from here. And let's click this report manager. Okay. Okay. So from here, okay. So right now, we're going to compare. On the bus 4, we provided the natural grounding resistor, right? The 600 amperes, the low resistance NGR, okay? Now, the result now, see, the three-phase fault is remain 12.998 amperes, okay? So, this is without 12.998, okay? And it's with resistor, okay? But now, the line to ground fault has changed. See here, it's now the value for line to ground fault is after we provided the NGR or natural neutral grounding resistor on the generator. Na line to ground fault now has decreased. Now it's 11.696 kiloamperes. It was 14.062 amperes as well. Okay, for double line to ground fault now is 12.495 kiloamperes, and earlier without the resistor it is 13.694 kiloamperes. Meaning the reason if the system is solidly grounded, the tendency the line to ground fault will be higher than the three-phase fault. Okay, and let's go again to our single line diagram. Okay, so from here we're not going to take run the minimum, because when we run this one, this is used only for the overcurrent release settings of the relay. Okay, okay. Thanks for watching.